All right, well, it's 9 o'clock now, so I guess we can get going. So I'd like to thank everyone for taking part in today's webinar and logging in. We'll be looking at our SLANE project. This has been an ongoing project since 2016. We're currently in the third phase of the project. A lot of sampling has gone into this since the beginning, so it'll be very interesting to see where we're at now. My name is Josh Fillion. I am a project specialist for RiverLabs. My role for this project is more to serve as a coordinator. The expertise for this project lies more with our presenters that are here with us today. Matt Windle, who is a research scientist for the River Institute, as well as Evan Rundle, who is a research assistant, but also our technical specialist. So just a bit of background on our organization. So we work for RiverLabs, which is a environmental monitoring and applied research program within the River Institute. A bit about the River Institute, that's our larger umbrella. We're non-for-profits, and we look mainly at dealing with research, education, and community outreach for river systems, more specifically the St. Lawrence River system. So today we'll be looking at our SLANE project, and our SLANE stands for Spatial Landscape Nutrient Estimate Model. And this is really the third version of our model that our presenters will get into later. So the River Institute and RiverLabs were situated in Cornwall, Ontario, which raised a few challenges this year given the COVID restrictions and mandates for travels and for just coordinating our sampling program. So it'll be interesting to see what comes out of this and potential future projects. And I just want to say a big thank you to MECP and specifically Tim Krusel and Andrew Chard for supporting throughout this project, as there was also some staff turnover on both the River Institute and as well as the MECP end, which provided some challenges. As you can see on the main screen, Mark McDougall and Louis Savard were some key players in generating the original model, and unfortunately they're no longer with us. So before we get going, just a few housekeeping items. Currently, all attendees, their mics are turned off. After the presentation is complete, we'll allow you to use your mics to ask any questions. If there's any pertinent questions that you don't want to forget about come the end of the presentation, feel free to use the chat function at the bottom of the screen, and that way we can run through all the questions come the end of the presentation. Following the presentation, we'll be sending out a short survey, just to hopefully receive a little bit of feedback on the webinar and the overall project. The answers are anonymous, and it will take you more than 5 minutes to finish. It's 5 questions total. And just as our last item is really that the web tool as well as this webinar will be posted on our website probably mid to end of next week. So for anyone that would like to follow up. So without further ado, I'm going to pass it over to Matt Windle, who's going to be our first presenter to run us through the project.
Thank you, Josh, for that intro, and I hope everyone can hear me okay. Josh mentioned I'm Matt Windle. I'm a research scientist with the River Institute in Cornwall, and playing a larger and larger role with this project. So my role today is going to be to walk you through the background on the development of the SLANE model, and then I'll pass it over to Evan Rundle, who's going to run through the actual web app tools that will be made available based on a lot of the modeling work that was done previously by Mark McDougall in the phase 1 and phase 2 components of this project. Next slide there. So thanks, Evan. So the webinar is just a little overview here. We have 3 parts to today's webinar. So the part 1 is just me talking a little bit about the underlying model development, some of the background, a little bit of information on remote sensing and spectral information, and then how that information was used to develop the model. And then I'll go through some model limitations as well. Like any model, this model does have some limitations based on the data sets we're using. For part 2 and 3, I'll be switching it to Evan to go through the previous version, excuse me there, the previous version of the web app tool that came out last year. And then Evan's going to go through the new version of the web app tool and provide an overview of that with some case studies as well. So the first part here, we're just going to go over the underlying model development and the information that was used to develop the SLANE model. So one of the biggest concerns we have for the Simcoe watershed and a lot of other watersheds throughout North America is the issue of non-point source phosphorus inputs to waterways, tributaries, lakes, and other water bodies. And it presents a real challenge to watershed managers and just tracking down and trying to manage these inputs because of the diffuse nature of non-point source inputs. So it's really valuable if we can come up with tools to help us identify hotspots that would otherwise be easy if we were dealing with, say, a point source. So just an effluent pipe, for example, discharging into a waterway. So there's a clear need to develop these tools that we can use for management purposes to look at very large scale pictures, to incorporate large areas, and then identify areas where there might be some sources of phosphorus, but then also looking at the mobility and movement risk potential of that phosphorus throughout the watershed. So that's what we've done with this project essentially, is that, and I'll get into some of the steps that were used for that, but this is essentially a tool that can be used to look at these non-point sources of phosphorus. Next slide. So remote sensing. We're probably all familiar with some aspects of this. I mean, we use this a lot in our daily lives with a lot of mapping elements that are just commonplace. And remote sensing as a tool is amazing. It can be derived from satellites, airplanes, drones, and a lot of the differences with that come down to resolution and the scale of the data products. So different types of remote sensing information can include radar, visible or invisible spectrums of light, LiDAR, which gives you really high resolution information on topography, the surfaces of the Earth. And but most commonly, we're talking about multispectral cameras in particular. And in this case, this is what we're focusing on for this project. And of course, light has all kinds of different a range of electromagnetic spectra. Very narrow bandwidth that is visible to us, but through sources such as satellite data, and in this case we're using there's a number of internationally funded satellite programs. One of them that's used generated by the United States is the Landsat series of satellites, and that provides multispectral imagery. So we have imagery that contains multiple bandwidths of light. And this is really great because we can use that to create some calculations and indices. So in this case, for the SLANE model, we're using actually the Landsat 8 satellite data and multispectral imagery from that source. Next slide. So Landsat and multispectral data contain many different bandwidths of light. And these different spectra can be used in combination to provide different types of indices. A really common one that's used to look at health of crops and vegetation is the Normalized Difference Vegetation Index, or NDVI. And that's really looking at the bandwidths of red light and near infrared light. And so healthy plants are essentially absorbing red light and reflecting near infrared light. They can't use near infrared light. It's actually damaging to them to absorb too much of it. So looking at those two bandwidths in particular, you can actually develop this index of plant health. So the more the healthier a plant is, essentially, the more near infrared light is going to reflect back into the air, into space, for satellites to measure. So that's an index that can be used to look at plant health. There's lots of other bandwidths we can actually use, though, that could also provide meaningful information. And this is essentially what the SLANE model did. So we've taken information from these multispectral bandwidths from the Landsat 8 satellite series, and Mark McDougall did a wonderful job over the first two phases of this project, where he took those spectra and essentially did some machine learning using a training data set. So the team went out actually over multiple years and collected a wide number of soil samples. And multispectral imagery can be used to look at, for example, algal blooms in lakes, and is used quite commonly in the Great Lakes, for example, to map out algal blooms, and including Lake Simcoe. But it's not used as often or as dedicated to look at the phosphorus content of soil in landscapes. And of course, that's really valuable when we're talking about soil that's potentially saturated with phosphorus from agricultural runoff and things like that contribute to these non-point source inputs into Lake Simcoe. So that was part of this model development that Mark went through with the SLANE model, where he took summertime imagery from the Landsat imagery, and then combined with training data sets of soil samples that were collected roughly at the same time. They ran that through some machine learning, and essentially the algorithms trained themselves to pair up the various combinations of bandwidths of light with the actual measurements of soil phosphorus. And that resulted in a quite high predictability of the model to predict phosphorus content in soil. So it actually worked out pretty well. And there was a lot of effort put into that modeling. And that brings us up to speed now in terms of being able to use these Landsat images to actually characterize the entire watershed in terms of predicted soil concentrations of phosphorus. And we're using that information now, that satellite-derived predicted phosphorus, as part of this tool, as one of the major components into this tool that we're going to be talking about as well. So the SLANE model is able to predict with fairly great accuracy and there are some limitations, but with fairly great accuracy, the phosphorus concentrations in the soil, the Simcoe watershed. But there's another component to the modeling, which is what is the risk of that? So if your soil contains phosphorus, but it's not mobile, it's staying put, it's probably not as much of a risk, or definitely isn't as much of a risk to become part of non-point source phosphorus runoff into Lake Simcoe. So there's other factors we wanted to consider as part of this third phase of this project. And ultimately we wanted to understand that risk. So what is the risk of this phosphorus, predicted phosphorus concentrations in terms of the risk it poses to flowing into Lake Simcoe and through the watershed? So that's what we're going to be talking about a little bit today in terms of this wonderful tool that's been developed. And I'll go through some of the different layers that this tool is built on. So there's three main layers. There's the SLANE model layer, again, where this is predicting using satellite imagery the concentrations of phosphorus in soil and across the watershed. The second layer this is built on is the Russell model. So this is the revised universal soil loss equation. And this is a model that was developed by the USDA. It's used in Canada as well, but essentially it incorporates various aspects of soil. So we have, I'll talk about that in the slide coming up here. That's essentially capturing how likely is the phosphorus to move across the landscape. And then we have the third layer as part of this web app, which is the total risk. So combining those first two layers and projecting and predicting where the high risk areas could be found. And then of course that can be used by watershed managers, conservation authorities, other interested parties to focus more efforts on these high-risk areas. So next slide there. The first layer I mentioned is the SLANE model layer. So what you're looking at right now is a predicted phosphorus concentrations across the Simcoe watershed. And this is just color coded. So you see those warmer colors, those reds and oranges would represent predicted higher concentrations of soil phosphorus. So that's our first layer there. And this is going to be part of the web app as well. So you can look at these individually and have a closer look interactively. The next layer here is our Russell layer. So this combines information about various components of information about the soil. So we have precipitation. Some of these values are fairly uniform across the watershed. Evan might cover that a little bit more in his part. We have another component of that that characterizes soil. We have slope, which is really important, right? So we have the aspect. So, for example, slope, high slopes could result in more runoff from various properties versus really low slope areas where there's probably not as much soil mobility. And then a really important component as well is the crop type. So there's incorporates different types of crop: corn, wheat, soy. The tillage practices as well are also important. So how those agricultural fields are developed, how the soil is turned over, things like that. So a lot of that's incorporated into this Russell model, and gives you an overall estimate of soil loss throughout the watershed. And you can see this is also color coded in terms of warmer and cooler colors. So the again, the red and orange colors would indicate areas that have a higher soil loss potential, and the kind of that darker green areas would be characterized as low soil loss risk areas. Next slide. We can combine these two, the SLANE model and the Russell model, to provide a total risk estimate. And this graphic shows the nice relationship between that. Essentially, areas that have predicted high phosphorus soil concentrations that also have high predicted soil loss factors are going to result in a severe risk. So, and you can also have high predicted soil phosphorus concentrations in areas that have low predicted soil loss. That will give you kind of a moderate level of risk as well. And then best case scenario is you have areas that are not being characterized as high phosphorus and then also have low soil loss potential. You can see that color coded in green. So these colors here are used in the following maps you're going to see as part of the modeling as well. So just keep that in mind as we move forward. The red and orange colors indicate higher risk moving forward. And here we have that combined risk map. So we have, again, those warmer colors indicating higher risk areas. And I'm sure this is no surprise to people that are very familiar with the watershed. But Evan's going to walk us through some of the web app tool that allows you to really get in there and see some of those finer details. And we're hoping this really helps understand the potential movement of phosphorus, the non-point sources, and also movement of phosphorus throughout the watershed. And as part of this project too, the phase 3 was interested in looking at the availability of this phosphorus to move through the watershed in relation to waterways. So we've incorporated the essentially the tributary data sets for the watershed, and a number of samples were taken as part of that as well, looking at focusing on areas that had high predicted risk, so hotspot areas of high predicted risk, and then conducting some field sampling last year to look at concentrations of phosphorus in the water adjacent to these high watershed areas, and then seeing if that matched our predicted mobility and movement of phosphorus throughout the watershed. We also, and we don't have a lot of, I don't think we have a lot of coverage of this, but this is going to be covered a lot more in our final report. But there was also some dedicated field sampling at the outflows of some of the major tributaries into Lake Simcoe. Again, paired up with upstream sources of high-risk phosphorus mobility. So basically field testing, validating this model to see if we could match up this high-risk flow of phosphorus into Lake Simcoe. So next slide. There are some limitations with the model. One in particular, the Holland Marsh area, does have some unique crop types. So when the SLANE model was being developed, it was looking at that training data set of hundreds and hundreds of soil samples throughout the several of the sub-watersheds. Some of those didn't quite pair up with the more unique crop types and tillage practices in the Holland Marsh. So the phosphorus concentrations in particular for this area are likely being underestimated based on that model. Next slide. Urbanized areas generally don't provide very meaningful reflectance and spectra from satellites. There's not a lot of vegetation in them to document. And also we're dealing with Landsat 8 data, which has a resolution of 30 meters by 30 meters. So the fine scale aspects of vegetation throughout an urban area are lost a little bit with that type of resolution. So essentially the urban areas throughout the watershed and the watershed are generally, we don't see as high a predictability accuracy with the SLANE model in these areas. Next slide. The other limitation is that we have naturalized areas. So there are forests and other undeveloped areas that do have, are probably likely being underrepresented by phosphorus in the soils. The nice thing about these areas is that they generally have very low risk of soil movement because of the anchoring nature of all the root systems in the soils, and they're not being developed or in any way. So generally these areas end up being low risk areas in the model. Next slide. The SLANE model was used, the data set that was used to develop the model was satellite imagery from 2017 and then again in 2020. So it is a little bit of a static view. Mark did some really nice work comparing differences in 2017 versus 2020 sat imagery that was used, and found very minimal differences. This likely has a high predictability moving forward for future years, unless we have large scale changes in agricultural practices, more development of natural areas. I mean, it would be a good idea to revisit this and input some new sat imagery in those cases, but generally the model remains very consistent across years. So that is good to know, and Mark did look into that as well. And I will mention too, in the 2020 analysis and development of the SLANE model, Mark, instead of using peak growth of different types of crops, he looked at minimum and maximum. So he took satellite imagery across the entire growth season in 2020 and used all those images to develop the model. So it had a much higher predictability compared to using a single Landsat 8 image. So that also gives this model a lot more robustness. Next slide. And of course, when we're using satellite imagery, there's always the potential of cloud cover to obscure parts of the imagery that you're trying to use. So sometimes it's also necessary to hone in on or to utilize imagery that maybe isn't exactly aligned with when the soil sampling was taken. And in some cases that was necessary. But again, the 2020 data set that Mark used that entire range of the growing season, all the imagery. So he was able to get around that a little bit with using a wider data set. Next slide. So that's a little bit of a summary. And again, you know, if Mark McDougall was here, he would be able to give you a much deeper, in-depth analysis and more details on development of the SLANE model. But I think that covers kind of the highlights of that model development, and we're certainly open for questions afterwards on that model. But really the focus of this webinar is this web viewer tool and the development of that tool. And so for that component, I'm going to pass it on to Evan Rundle here. And Evan's been the main developer of these two viewers. So he's very familiar with the layers and the GIS components of this. So you're in good hands here. I'll pass it to you, Evan.
All right, thanks. So as Matt just said, I'm Evan, and I've been providing technical support to the project for just over a year now. So I'm going to jump right in and start describing our web viewers. The first web viewer that we developed in 2020 was this web application. And essentially what it was you would get brought onto this home screen that you're looking at right now. And you could explore the map, zoom in and out, activate and deactivate different layers. Also at the top right, there was links to different crop types where you could explore how crop types and tillage practices could influence the risk factor. But the main issue with this web application that we found was that it was not super intuitive, and there was also no way to provide any background information or supporting documents to the maps you're looking at. So what we did this year was we converted the format to a story map, which I will preview for you now. That looks something like this. And already you can see it's a much more inviting looking website to visit. As you scroll down, you will see these headings that you can click on and zoom to any part that you're interested in reading about. And if we move past that, we've got the introduction. And this is stuff that Matt has already covered in his slides, but it's basically just some background about the project, how long it's been going on, and why and where we're doing it. And then past that, we come to the map of combined risk factors. Now, this is the map where we combined the SLANE data with the Russell II model. So this map is the one that shows you the risk of phosphorus running off and ending up in the water. So here's the map itself, and the legend that Matt showed you is just below it. And this map is fully interactive. You can move it around, you can zoom in and out. Got a box in the way, but you can zoom in and out. And even at the top left corner here, you can type in an address if you're interested in looking at a particular property or area. So looking at the map, you've got the combined risk model outlined in these colors. And these black lines actually represent the sub-watersheds of the Simcoe area. And moving past that, now we're going to move into some background information, which again, Matt has covered in his slides, so I won't go into huge detail about it. But essentially, we're going to go into the layers that go into creating that combined risk factor, which are the SLANE model. And this was our model of phosphorus soil phosphorus concentrations that was developed by Mark and used satellite imagery. Now, again, this map is fully interactive. You can zoom in, find different places, look at any properties you might be interested in. And your legend is over here on the side with some supporting information and some facts about the project. If we move past that now, we've got a description of the Russell II model, which is the soil loss model that we used, and some examples of layers that were used in this model. So the layers that go into the model are the rainfall, crop type, and farming practices are applied as constants, which look like the bottom right image here. They just look like a homogeneous block kind of applied to the whole area. The K factor represents the soil erodibility, which is basically how packed together or the coarseness of the soil. It's a factor that represents the likelihood that that soil moves from where it is. There's also the slope and slope length. So slope is obviously the slope of any given area, and the slope length, the LS that you're seeing at the bottom left, is a factor that describes for how long of a distance that slope is maintained. So that would be giving more inertia to the water that's passing over the area. And if you're interested in learning more about the Russell II map, we've provided a link to the Ontario government page about it here. And you can visit that to kind of read up on what this model is all about. So then just below that, we've got this neat little function that's called a slider. And what it's showing is, if you move it this way, you're seeing the SLANE model, which is our phosphorus concentrations predicted from the satellite imagery. And if you move it this way, you're seeing the combined risk factor, which is the combination of the Russell model and the SLANE model, giving you the risk of phosphorus actually entering the water. So this is just a neat little function to scroll over the areas and see how the map changes based on the application of a Russell II model. So the web application from 2020 is also linked right here. And this application, again, looks like this. So this is the main page, what you'll see when you click on that link. And this pop-up box is just explaining where certain features are located. So what it's saying is that you've got your legends up here. You've got links to specific other applications based on crop types here. And you've got your layer activation and deactivation panes here. So on this home page, you've got the SLANE model and Russell II model outputs. And if you click on one of these maps, it brings you to a new page where you've got the combined risk factors for any given crop type. So the one I've just clicked on is grain and corn. And in this pane now, we've got the tillage practices. And by default, fall plow is active, but you can switch that on and off and select any layer you're interested in seeing. And again, this map, all of the maps you're seeing right now are fully interactive. You can zoom in and out, you can find addresses, basically get a better idea of what's going on. So that's another tool, the past tool, you can explore that. And I'm just going to quickly talk about the field validations for 2021. So up to this point, the web application and the model that we have is had a lot of validation going into the phosphorus concentrations in the soil. And now the 2021 goal was to validate if what we're seeing in the soil and our risk factor model was actually translating to the concentrations of phosphorus that we're seeing in water. So for 2021, we took water samples in the locations that you're seeing on the screen. And again, this is a slider function. So if you slide it this way, now you're seeing the concentrations that we observed in October. And we can zoom in and explore these, any areas that you're interested in. And then if you slide it the other direction, we've got the concentrations we observed in November. So one of the interesting points that we've noticed is that for the majority of the sites, well, all of them except this one point, the concentration in October was higher than the concentration of November, which is exactly what you would predict for any natural system. But as you can see, this one was actually a lower concentration in October compared to November. So that was a bit confusing. But if we zoom in, you can see it's right next to this, our sampling point was right next to this golf course. So what we're thinking is there was a late fall application of a lot of fertilizer to this golf course, resulting in this high concentration. Not a super important finding, but very interesting for just looking at the points. And below this map, you've got the legend for the points that you're seeing on the map and some descriptions of the field sampling. An important thing to note is that the legend for the phosphorus concentrations in the water, these groupings, these concentration ranges are actually based on the trigger ranges for total phosphorus concentration that decide the trophic state according to the Ontario Water Quality Guidelines. So we've got the highest range here represented by the star is actually hyper-eutrophic, followed by eutrophic, and then descending all the way to hyper-oligotrophic in this blue color. And as we continue scrolling through here, we've got descriptions of the sampling events. I won't get into too much detail about that, but feel free to come back and read about it if you'd like to. And a little description on how we actually selected the sites. And how we selected the sites was that we mapped out these red points, which are predicted areas of high phosphorus. So we classified these as hotspots, and then used ArcGIS to model the flow path from these points into the lake. And we sampled along these tributaries. So now I'm just going to, well, that's the web application. That's kind of the end of it. So I'm going to move back into my presentation and continue with some future directions for the project. So the tool was intended to be used as a tool for watershed management and planners to target areas that need restoration or to apply best management practices to the land for high-risk areas. And for that, we need to really make sure that the model is giving us accurate information about when and where the soil or the phosphorus is entering the watercourse. So I'm going to go through a theoretical case study of two different methods of validating the model. So I'm going to be looking at this area right here, which is some high-risk area that's draining into the east branch of the Holland River. So I'll just zoom in on that, and here are the watercourses running through this area. And theoretically, the phosphorus and the soil running off from this little triangle that I've highlighted are all running into that East Holland River. So I'm going to focus on that river for now in this example. And to validate this, we just want to make sure that as the water is moving through this area, we are seeing phosphorus entering. So these are our field measurements from 2021. We took this water sample and we did actually classify this spot as eutrophic, which for October and November is a really high measurement for phosphorus. If we wanted to validate this and make sure that this point is actually accurate, we would do some more sampling that could look something like this. So I've plotted out 7 theoretical sampling points along this river. And what this is going to do is give us an idea of what's happening upstream from this high-risk triangle, what's happening within the triangle, and then what's happening as the water's moving through the lower risk green area. So if our model was accurate, we'd expect to see something like this, where the concentration moving into that area down at the bottom of the screen is the lowest concentration. And as it's moving through the high risk area, we'd expect to see phosphorus going into the watercourse. Now, as it's moving through the low risk area, there's 2 possible things that could happen. it could potentially, the concentration could remain constant as the water is moving through, or we could see the concentration decrease. And this would be due to the sediment settling out of the water being diluted by cleaner water sources coming from the low risk area, or by uptake of the phosphorus by plants and algae as the water is moving through. So those are the two possible outcomes we would expect to see if the model was accurate. If we ended up with results like that, we'd also want to do some statistical validation. So I'm going to use the same point as an example. And what we would want was some consistent field sampling of this point to get an accurate idea of how much phosphorus is in this location. Then from there, we're going to look at all of the tributaries that are flowing into that point. So that would look like this. And once we have this catchment mapped out, we would want to look at two different things. We'd want to look at the relationship between the phosphorus concentration that we measured at that black dot and the ratio of high to low risk area within this catchment. We'd also like to compare the concentration to the total amount of high risk area in the catchment. And this is because it will give us some idea of what the phosphorus is actually doing as it's moving through the catchment. So theoretically, if phosphorus is entering the watercourse through this spot that I'm pointing at down here, and it's making it all the way through here to this black point, we would expect the concentration of phosphorus at this black point to be very closely related to the total high concentration, the total high risk area within the catchment. But if this phosphorus is going into the watercourse, and as it's moving through, the phosphorus is becoming diluted and settling up and being uptaken by plants, we would expect the concentration here to be more related to this ratio of high to low risk areas. And this is because the green areas, the low risk areas, are going to be offsetting these higher risk areas when they're farther away from the catchment or from the monitoring point. So once we've looked at enough catchments and done this same monitoring, we can monitoring and calculation, we can actually do a geographically weighted regression, which would give us a statistical kind of backup for saying how accurately the model is actually representing phosphorus entering the watercourse. Yeah, so for recommendations of next steps, obviously the model validation is really important. The two examples that I just described are what I would recommend. The high risk targeted sampling effort was that first one with the 7 points along the tributary. And 7 points is a lot, but you could theoretically do it with 1 point upstream, 1 point in the high risk zone, and 1 point downstream. But the more sampling, the better. And the statistical analysis of the catchment phosphorus relationships, the example I just showed on the last slide. And that would give us a really good understanding. Looking at all of these things would give us a really good understanding of what's actually happening to the phosphorus, if it's lining up with our model, and if it's actually being transported from these areas into Lake Simcoe. One thing that could help us with this is incorporating existing water quality data. So if we could get data from watershed management or conservation authorities, it would be really easy to incorporate existing water quality data and use it for these modeling efforts and statistical analysis. The other thing would be the involvement of citizen scientists. And this is just to reduce the cost of sampling. We attempted to get some citizen scientists involved in 2021, but due to COVID and travel restrictions, we we didn't get many results from that. So it would definitely be worth trying again as restrictions are lifting and we're moving forward into the next sampling year. So with that, I have explained all that I was planning on explaining. So I'd just like to thank everyone else who worked on this project. A lot of people developed the model and put a lot of work into this before I even started working on it. And a lot of people were doing the field work, Josh and Jamie, and then Luke and Crystal were doing the lab analysis. So I'd just like to thank everyone who was involved with the project. And it's a lot of names, so I won't go through them all, but I'll move into questions now. And you can see our contact info on the screen if you feel like you have some questions you'd like to reach out to us on email with.
All right, well, with that, I'd like to say thanks again to everyone who chimed in this morning, and have yourself a great weekend.